Hello, in this presentation we'll talk some more about how triangles in a 3D image get mapped onto a rendered image on the screen. So in this setting here we've got a three-dimensional scene which is typically rendered as triangles with all shapes are typically going to be rendered with triangles, possibly with lines as points as well, but for solid objects we usually think of them as triangles. And the triangles model the surface of the objects. So in particular, we talked about the sphere last time. If we have a sphere, we broke the surface of the sphere up into triangles, and we then let the triangles approximate the smooth shape of the sphere. And it's also going to be rendered with a view or camera position and direction. So in other words, someplace there's a viewer, which I'll draw with a sort of stylized eye shape. This is meant to be an eye or a camera. And the viewer is looking in this direction at triangles in the scene. And we want to take those triangles in the scene and map them onto the view plane, onto the image as seen by the viewer, namely what we would render, say, on the computer screen or in the photograph or whatever. Okay, and so in that way we change the 3D triangles into a 2D image. But now, obviously not all triangles are visible to the viewer. First of all, there could be a triangle behind the viewer. Right? So here's a triangle behind the viewer that's not visible, sheerly because the viewer is looking in the other direction. Or then there's another, here's a triangle. I really mean for this triangle to be on the inside of the sphere. So the viewer is looking at this front face, and if there were a hole in the sphere, would look over and see the back face of the triangle on the other side. So remember, all triangles come with front faces and back faces. They're given by the counterclockwise rule normally. And we could just say here that we can call and call means the same thing as discard triangles that are not visible to the viewer. And so some of them get automatically called, like the ones that are behind the viewer in the opposite direction that the viewer is looking, automatically get called by OpenGL. It's taken care of for you. You don't have to do that. But then other ones, like here's a triangle that's on the inside of the sphere, facing inward towards the viewer, but the viewer is outside the sphere, so we know ahead of time that the front side of the sphere is going to hide the back side of the sphere, and so we can also call back faces in this case. So when rendering closed, think of solid objects, surfaces, we can also call back faces. We can also call back faces. Of course, that assumes that we've correctly modeled the surface with the front faces facing outward from the surface and the back faces facing inward of the surface. And it also assumes that the viewer is outside of the solid objects, that somehow the viewer hasn't gotten inside the sphere. If the viewer got inside the sphere, you'd be able to see the back faces, of course. So let me talk a little bit more about culling. So pretty much I've already described culling. Let me just give you the OpenGL commands that are used. By default, it doesn't cull back faces, but you can enable culling of back faces by calling GL enable GL cull face. That's GL underscore cull underscore face. And that'll turn on culling. And you can also specify which faces are called. By default, the faces that are called are the back faces, GL back. This is the default setting. But it could also call front faces, or in fact both front and back. You can also do GL cull face, GL front, or GL cull face, GL front and back if you just want to cull all the triangles. Okay. When you want to turn culling back off, you can use GL disable, GL cull face with 2 underscores. You can also, okay, good. You can also change the conventions on counterclockwise versus clockwise. If you use, so GL front face, GL CCW, this is the default setting. This is what was described in the previous video, is when you look at the first triangle in a triangle strip, or the triangles in a triangle fan, or standalone triangles, if the vertices V0, V1, V2 are in counterclockwise order, that's the front face. And you can, however, also change the conventions to make the opposite face the front one, with calling GL front face, GL CW, CW for clockwise, CCW for counterclockwise. Okay, and again, we're culling, when we do this, the purpose is when we know that the viewer is outside of a solid object, and we know the front faces are facing outward from the surface of the solid object, and the back faces therefore are facing into, we can automatically cull the back faces and avoid the extra work of rendering these things inside that aren't visible. There is, however, a second reason why this triangle on the inside is not visible, and that's because the triangles on the front of the sphere are hiding to the viewer the triangles on the back of the sphere. So this is called hidden surface removal. If a surface is hidden from the point of view of the viewer because of triangles in front of it, we also don't want to show it to the viewer. So I want to talk about next about how to detect hidden surfaces. So for hidden surfaces, we're the setting where we're rendering a lot of triangles in 3 space from the point of view of the viewer, and we want to figure out which triangles are closest to the viewer that are being seen by the viewer, and which ones are being hidden by triangles that are closer to them. So the point being then, if some triangles are in front of other ones, they hide the other ones, and we want to determine that fact. So there's 3 basic methods for this. So method number 1 is what I would call geometric analysis, which means actually looking at the triangles and deciding how they overlap. So here, loosely speaking, you would do the following. Consider all pairs of triangles in the scene. Figure out how they overlap each other. And then render only the visible parts. So the kind of things that could happen is I could have, let's get some colored markers here. So for instance, I could have a green triangle that's being partially blocked by a red triangle. So think if there's a green triangle in the scene, and there's also a red triangle, and the red triangle is closer than the green triangle, well, we would say you don't see the green triangle at all. Instead, you see the red triangle. So this would get, the green, say, gets filled in with green, the red gets filled in with red, and you would see something like this. So with the geometric analysis, you would figure this fact out, and since we're only rendering triangles, we'd probably break that part of the green triangle into 2 pieces. We'd render the green triangle as 3 smaller triangles, and the red triangle could just be rendered as itself. And of course there's many different ways this could happen. I could have the green triangle blocked in this way, that's meant to be a straight line there, by the red triangle. So here, there's the green parts visible here, and the red parts visible in here. And we could even have a more complicated thing where the green triangle and the red triangle interpenetrate each other. Let me see if I can draw that here. So here's the green triangle, and it's not entirely behind the red triangle. The red triangle sticks into it. So the red triangle, let me draw it sort of at an angle, and it sticks in, but try that again. It sticks in, but it's not entirely sticking in. It's like this. And so we have something like this. The red triangle is penetrating into the green triangle, like my hands are penetrating each other with fingers. Okay, so we have to figure out all those things if they happen and render the image correctly. So there's obviously some disadvantages to this. The disadvantages include you have to know all the triangles ahead of time. So you have to already have all the triangles before you can do this analysis, because in principle you want to do all pairs. There's ways to make it faster. You don't have to literally do all pairs. But then you also need to write a fairly sophisticated algorithm to make this all work reliably. Okay, so it's not all that easy to code. You also have to redo this every time, say, the view position moves. You must redo the work whenever things move, in particular whenever the viewer moves. So it has a lot of disadvantages. So method 2 will be the painter's algorithm. So method number 2 is the painter's algorithm. And the painter's algorithm has a very simple idea. You sort the triangles so that the furthest triangles from the viewpoint or the camera get rendered first, and then you successively sort closer and closer triangles to the viewer, and you let the closer triangles overwrite the further away triangles. So we render all the triangles, but we only end up seeing the ones that are not hidden by the closer ones. So we sort triangles by the reverse distance from the viewer. So further away ones come first from the viewpoint. And we then render farther away triangles first, and closer ones last, and the closer ones overwrite the ones they hide, or the portions of the ones they hide. So a picture of this would be, we have two triangles, green triangles further away than the red. So the green triangle would get drawn first. Even the portions of it that will be hidden get drawn first. Now when we say draw this, we're drawing it into an array of pixels. So when we draw a triangle, the triangle is specified by the vertices, and then each triangle covers some pixels on the screen. And we just, of course the pixels aren't quite triangular, but we just draw the pixels green that are covered by the green triangle. And then we come along and we draw a red triangle, and it's closer. So maybe the red triangle is here. and it's closer than the green triangle. So what we do is we just draw the red triangle too, and what that does is it overwrites the green triangle's pixels, and we just fill in the red triangle pixels. And in this way, we just overdraw. The hidden triangles are drawn but then written over, so you don't see them in the end. So to a certain extent, this is how many painters actually operate, or some painters operate, and this is called the painter's algorithm. So if a painter is drawing a scene, say you've got a Renaissance scene with a castle with a horse in front of it or something like that, the painter might draw the background, the mountains and the sky, and then even the part that's behind the castle, and then on top of that draw the castle, and then in front of the castle and on top of what he drew for the castle, draw the picture of the horse. And so this way the painter can draw each component separately. He can draw the background without having to worry what the castle looks like particularly, and he can draw the castle without having to worry about what the horse looks like particularly. And so this inspired the name of the painter's algorithm here. So there's obviously some advantages to this. One is it's elegant and simple-minded, right? You just sort and draw, and you don't worry particularly how they interact. You just overwrite, so you don't have to think about it. The disadvantages are you do have to have all the triangles first and sort them, or have some other method of sorting them. Right? If somehow you know that some things are further away, you might just render them first and then render the closer things second. And again, if the viewer moves or the object moves, you have to redo the sort. So that's a disadvantage. Have to redo the sort. Have to redo the sort. Okay. There's another disadvantage, is it may not be possible to sort consistently. So it could happen that we have three triangles arranged so that each one covers the next. So I could have three triangles like this. Here I'll have a green one like this, and I'll have a red one like this, and a black one like this. And it could be that in all three cases, the thick part of the triangle is closer than the thin part of the triangle. So this part of the black triangle blocks the red triangle. This part of the red triangle blocks the green triangle, and this part of the green triangle blocks the black triangle. So the triangles are interleaved. The black one is over the red and under the green is over the black and under the red is over the green and under the black. So here there's no way to sort them. You can't draw the red first, or the green first, or the black first. So in this kind of thing, the painter's algorithm will fail. Not a particularly common thing, but it's definitely a disadvantage. So there may be no way to consistently sort by distance. Okay. So this will take us to the third method, which is the depth buffer method. So for the depth buffer method, this really takes advantage in a very crucial way of the fact that we're drawing into pixels. So normally when we're drawing a triangle into a rectangular array of pixels, we identify the pixels that lie underneath the triangle, and we give those pixels, say, the color that goes to that triangle, possibly shaded, smoothed out, or something like that. And what we do now is we give each pixel two values, not just a color value, but also a depth value. So each pixel, the depth value is the distance from the viewer. Each pixel in the output image stores a color value. That'll be the color that the pixel is set to, something in the red, green, blue color range usually, and a new thing, a depth value. And the depth value is essentially the distance from the viewer. We'll see it's not exactly that, but it respects the distance from the viewer. The distance from the viewer, the distance from the camera. And so what we'll do is, when we're drawing a triangle, we render the triangles in any order. Two pixels in any order. They can be completely unsorted. And when we do this, we prepare to write into the pixels that go with that triangle. So when we render a triangle, and we just compare the depth values. So let's see. So when we render a pixel of a triangle, we compare its depth to the previously written depth. So there may have been earlier triangles that also wrote to that pixel, and whichever one was closest stored its depth value. And now when we get a new triangle writing to that pixel, we compare the depth, that is the distance, of that pixel on that triangle to the viewer. And if that depth value indicates that it's closer to the viewer than the old value inside the pixel, we overwrite the pixel's color and depth values with the new color and depth values. Otherwise, we keep the old color and depth values because that old value came from a triangle that's hiding this pixel of this triangle. And we keep the closer pixel color / depth values. So you can see there's, again, lots of advantages to this. It's a very simple idea. It depends heavily on the pixelization, but the advantages are, right, it's simple. You can render triangles in any order. So we don't have to sort. We don't have to do any geometric comparisons or geometric analysis. We can just render the whole scene. If the viewer moves, we can still render the triangles in exactly the same order. We don't have to change any of that. It's amenable to parallel computing. So we can do this in parallel on lots of different processors at once. In particular, it matches well the shader model, where the general processing unit, the GPU, has a lot of small shaders, and we can just have a lot of vertices, a lot of triangles, and a lot of pixels, really a lot of pixels, all being processed more or less in parallel, pipelining the results from one stage to the next. But it doesn't matter which triangle is being handled first. If they get a little bit out of order, the depth buffer method takes care of that. There are some disadvantages, of course. Nothing in life is perfect. So disadvantages include mostly that you need extra memory for the depth values. So depth value is usually 32 bits. So you need an extra 32 bits per pixel on your screen. 32 bits is a common thing. So, you know, there could be millions of pixels on your screen, but memory nowadays is pretty cheap. So memory is cheap, so I'll just say that's not such a bad advantage. This was a bigger disadvantage a few decades ago when memory was more expensive, but nowadays it's quite cheap. We also have inherent in this, but actually any transfer to pixels, is what's known as aliasing problems. Aliasing problems we'll talk about later on. It's any time we're converting from some analog or perfectly smooth process to a digital process, or discrete process. So here the analog or digital or smooth part is that triangles have perfectly straight edges, and we're mapping them to a rectangular array of pixels. So these are discrete points on the screen. So we don't have a perfect matchup between triangles and pixels. So that's a disadvantage with any process that goes from triangles to pixels, but there's a few extra ones that can kick in here. We'll talk about that later on. So finally, on a somewhat unrelated topic, I want to talk about animation, how we give the appearance of things moving on the screen, or in movies, or whatever. So basically, to give the appearance of motion, we show a succession of still images changing very rapidly. And your eye, your visual system, just makes that look like a moving image. So probably most of you have done a simple example of this maybe back in grade school when you made little stick figures, you drew by hand on something and on the pages of a book or something like that, and you flipped the pages by and it looked like it was moving. So that's a very simple example of that. But in fact, this is the same process, the same principle that's used in movies. So movies traditionally had 24 frames per second. Frames per second. Digital movies now have flexibility of more frames. So like the Hobbit movie had 40 frames per second, I think it was. 48 frames per second, sorry. The Avatar 2 had 60 frames per second. So this higher frame rate makes for smoother looking motion. Computers will typically have 60 frames per second. Also, computer games will usually have 60 frames per second or higher. In fact, games often try to go to 120 frames per second. So the higher frames per second makes a smoother looking motion, but the basic idea is we're showing a bunch of still images. Like when you pause a movie, you see a still image, and the movie is actually a sequence of still images that gives the motion in your eye. So the way this is done on the computer is in OpenGL, we maintain 2 frame buffers. A frame buffer means a buffer where we write an image. There'll be the front buffer, which I'll draw sort of as a rectangular thing. And this is the current image being displayed on the monitor or wherever. And so as we're animating a scene, we render a scene at one point. It's in the front buffer, and that's what the user's seeing. So while the user's looking at that, the computer is working on a back buffer, which is a completely independent section of memory. And this is the next image, which is being formed, being created. So for instance, with the depth buffer method, if you were to look at the back buffer, you would see triangles start appearing and then other triangles overwrite them because the depth buffer method overwrites them. And then eventually the whole scene would be there. All that should happen in less than a 60th of a second. And then once the next image has been formed, we swap the 2 buffers. The back buffer becomes the front buffer becomes the next back buffer. We clear the back buffer out, the new back buffer, the old front buffer out, and we start rendering the next image after that. So we swap buffers, which doesn't mean really that we swap the data in the buffers. We just swap the buffers, their roles, to switch the back buffer and the front buffers so that at any point the user is just looking at a fixed still image. The other back buffer is changing as it's being created, but the user doesn't see that. And this is the method used to create animated motion. All right, that's the end of this video, so thank you very much.